All right, welcome back. I'm just going to, it's pretty late right now, so I might make a few more mistakes than usual, but I want to go ahead and finish this off so that we can start learning about quantum mechanics. And I also want to get to the end of the story. So the shapes that the electron waves can take are what we're going to finish talking about, and we're actually going to talk about the shape the periodic table takes. On top of it all, there's a little YouTube song I'm going to play for you called The Shape of You. But we will get to that in a second. Okay. So the potential energy between two charges, remember that we have an equation. I showed this very quickly on the first day of class today. We actually don't use this equation very much in this class, but we use it right here. The equation between two charges is the size of the two charges, Q1 and Q2, and then you divide it by the radius between the two charges, which is r. All the other stuff is constants that depend on the context and things like that. So what this really is this will work for static spheres, but it will also work for very small spheres, for protons and electrons. And in fact, because protons and electrons have the same charge, they balance each other out very nicely. They have very different masses. And so what you can do is you can actually say, okay, well, Q1 equals E, the charge on an electron. Q2 also equals E. And so when you multiply them together, you get E squared. So really what this is for a proton and an electron is it's going to be some kind of Z times, Z is the number of protons, and the thing that we'll do is we'll keep things simple. We'll keep Z equal to 1 because we'll just deal with hydrogen. And let me tell you, that is actually pretty tractable with hydrogen, but it gets a lot more complicated to calculate these things, even with helium and lithium and things like that. So we'll keep it simple. We'll keep Z being 1, and that means that the top of this equation is just going to be negative E squared. By the way, does it make sense that the potential is negative? Remember that a lower V is a more stable situation, and if you have opposite charges, you're going to have plus E times minus E. Plus E times minus E is going to, and by the way, the charges themselves are on the actual. So I'm already being too tired to say this exactly right. But the reason why it makes sense that the potential is negative, this is the case where you take electron charge Q1 is negative E, and the proton charge is positive ZE. You multiply those together and you get a negative number, negative ZE squared. The reason why that makes sense is because a negative energy makes sense in this case because a negative energy is, stable, and when you have a plus charge and a minus charge interacting, that's going to be pretty stable. So what you really do with this is you actually take these numbers and you plug this in. This is actually the equation that you use. It's just a version of this Q1, Q2 over R equation. And you work out that what the energies are. The V is the energy of the level of the box that will fit. Remember the particle in the box that we had? The Y scale on that is our V. And so we can figure out what our V levels are for certain shapes of waves. And remember, because the waves have to be tied down at either end for the particle in the box, we only get certain levels of V, depending on the number of nodes we have, the amount of energy that's in. As we go up, we get more complex waves, but at the bottom we have pretty simple waves that are tied down in very simple ways. So the thing is, this is actually how you do the math. And once you do that, the wave function is what you determine from this. You determine the wave function psi, and I've got it for you right here. The wave function for hydrogen is this right here. It's e to the negative r over some constant. The r is the radius for how far away the electron is from the proton. The main thing I want to show you, here's our calculus right here. Remember we talked about what e to the minus x looks like. What it looks like is it looks like a curved line that goes down. E to the minus x will be very high when the radius is low, and then it will quickly sort of curve down to be much lower. That is psi. Remember to get the equation where the electron is going to be to get the position, we take psi squared. And so you see right here, if you take psi squared, if you take this and you square it, then you end up with this sort of shape where you have the maximum place where you expect the electron to be, the radial distribution, really close to the proton. You don't expect it to be very far away, you expect it to be very close to the proton. And in fact, if you work out exactly what that looks like in 2 dimensions rather than 1 dimension like we have right here, what you see is the negative electron is happiest right here in the purple part, right on top of the proton. And it takes a nice spherical simple shape. The simple levels have a simple shape. So this is the case for the energy level of n equals 1. Remember on that previous thing, the lowest level was n equals 1. This is the simplest 3D wave that an electron can make around a proton. Now you might have noticed there's also an L there. Because we are not dealing with a one-dimensional situation, we're dealing with a three-dimensional situation, we have multiple boundaries and we have multiple boundary conditions, and each of them has its own number. Each of them works in the same way as n, but each of them has its own effect on the wave. So this is where we get to the weird 3D math, and you're going to have to trust me on some of this. But there are 3 boundary condition numbers, n, l, and m to the l. N is the principal quantum number, and it's the one that's sort of easiest to visualize and understand. Basically, it's based on the boundary that the wavelength cannot be infinite. There's no such thing as an infinite wavelength electron. That doesn't make any sense. It's the kind of thing that really doesn't make any sense, and so we exclude it from this situation. So that boundary results in the n equals 1, 2, all the way up to infinity that we have, that we showed you, that looks like the particle in the box. These are very simple allowed values, and you can't have n equals 1.5 because waves cannot do that. Now the other boundaries are a little bit more complex. The orbital, the L angular, the L number is the orbital angular quantum number, and that happens because the wavelength must match itself at the poles of the atom. Okay, so that's some 3D math type stuff. But the main thing is that L can be quantized as well. L cannot be anything other than an integer. It can be 0, it can be all the way up to n minus 1. And so for n equals 1, there's one option for L, because L has to be 0. For n equals 2, L can be 0 or 1. And on up from there. Finally, there's a third boundary condition number, which is m sub L. It's called the magnetic quantum number. And it's because the wavelength must match itself around the equator. And that's, again, a three-dimensional math type thing. But for L equals 1, m sub L has 3 possibilities. For L equals 0, m sub L can only be 0. So m sub L can only be, and if you look at the bottom here, m sub L can be equal to L, L minus 1, L minus 2, all the way to negative L. So for n equals 1, we only have one option, L equals 0, and m sub L equals 0. But then when we get to n equals 2, and L can be 1, then we can also have possibilities for m sub L from L, L minus 1, and negative L. That means for L sub 1 we have 3 possibilities. And it turns out that those 3 possibilities correspond to our 3 dimensions. The 3 possible ways to orient yourself in 3 dimensions is you can orient yourself along the x-axis, along the y-axis, and along the z-axis. 3 axes, 3 possibilities for orientation, and 3 magnetic quantum numbers. So that's a lot of math, but the main thing is those are all quantized and they only can be certain values. So what if we do the same thing we did for the n equals 1 level, and let's do it for n equals 2. Well, for n equals 2, now we have down here n equals 2, L equals 0, n equals 2, L equals 1. For n equals 2, L equals 0, we get something that looks exactly like n equals 1, L equals 0. We get basically a big purple. We get an exponential function for the radial wave function. We get a simple distribution. for the psi squared radial distribution, and then we have the radial wave function, which is just that the electron's basically sitting on top of the proton. Okay, it's just a sphere where are most likely to find the electron sitting on top of the proton. But the n equals 2, L equals 1 possibility ends up looking a little bit weirder. The radial wave function looks a little weird here. The radial distribution is a little bit farther out, although the wave function looks different. And what's really interesting is when you take this out and you work it out in 3 dimensions, you end up with one node, so it has this little dumbbell shape, and you have 3 possibilities. You have it aligned along the x-axis, it aligned along the y-axis, and aligned along the z-axis. And you can see that you have those 3 p orbitals, and those are called the p orbitals. So remember from organic chem that the p orbitals, there's 3 possibilities: up, down, and sideways. Up, down, back, forth, and sideways. Okay. So because the p orbital has a more complex shape, it has more possible orientations, and it turns out that it has 3 orientations. Those go with the 3 m sub L numbers. And you see that we've gone up in energy when we go to the p orbital, and we have 1 node, where with the s orbital we have 0 nodes. There's a node there, there's a node there. Each of the p orbitals has a node. So let's keep going up. Let's move to n equals 3. And n equals 3 has an s level that's simple, has a p level that's more complex, and then it has another possibility where the m sub L is now from 2 to negative 2. Those are 5 possibilities: 2, 1, 0, negative 1, negative 2. And so that means that we have 5 possible orbitals at the 3rd level, which is the 3D orbital level. And look at that. If we plot out what they look like, we get 3 possibilities that each have more lobes. They have more antinodes. It looks like they have 1 node here, but there might be more hidden there. I don't really know the math well enough to be sure. But when we bring them up here and we look at all the d orbitals, when we get to the 3rd level of energies, we have 5 possibilities. First level of energy, 1 possibility. Second level, 3 possibilities. 3rd level, 5 possibilities. Those are pretty simple numbers. And the main point is that as you go up in energy, you get more possibilities. And not just any more possibilities, not just having like bigger of the same, but you get more complex shapes, and the shapes go up by odd numbers. So as we go up in energy, we get more twists. So we go n equals 1, n equals 2, we have 3 possibilities. N equals 3, we have 5 possibilities. So you can guess the pattern here, right? For n equals 4, which would be the f orbitals, we have 7 possibilities. And we can go on with this all the way up. We can say there's 9 possibilities, 11 possibilities. It actually just keeps going like this, because again, remember that the rules that I showed you are the rules that apply to all electrons, no matter how much energy you pump into them. You get more nodes, more complex shapes, but you are only going to have the number of possibilities that we show you right here. And so this is like if you pluck a string, you get more nodes at higher energies. So if you pluck it harder, put more energy in, you get it vibrating more and you get more nodes. It's the exact same with electrons. And just like the strings are quantized in 1 dimension, the electrons are quantized in 3 dimensions. 1, 3, 5, and 7 possibilities, and all the way up from there. So it seems to be, if we really can do the math, we have to do a little more work to actually do the 3D math to work out exactly what they look like. But I can show you where somebody has done that math and what it looks like. This is called the grand orbital table. And if you look at this right here, you can see right here it has the different quantum numbers, and it has the number of possibilities at each level. And so you have, here's your 1s level, here's your 2s level, and here's 2p levels. And then you have your 5d levels, and you see that how you keep going up. You keep going up, and as you go up, you get more nodes, you get more lobes, you get more, vibrations out of the electron in a certain sense. And you can go all the way up to electron configurations that would be super high energy. You're not going to have these in any atom on the periodic table. But if you have, I believe that, so n equals 1 is S, n equals 2 gets to the P level, n equals 3 has the 3D level, n equals 4 has the 4F level, n equals 5 has the 5G level. And I think they just give up from that point and they just start adding. So I think that n equals 6 has the 6H level, and then you keep going on up from there. But this is what they would look like. I don't know what it takes to put this much energy into an electron, but it's pretty easy to calculate for one electron and one proton. And you see that they've gone all the way up to n equals 10, and you get some pretty crazy balloon animal looking stuff from there. So you can scan through this and you can just see what the physics people have done for us. And you can thank them someday when you talk to them. So this is how the molecular shapes work. And that is why I am going to suggest, well, actually, I'm going to give you this right here. Just go to Acapella Science and do the molecular shape of you, Ed Sheeran parody. And you can find it. I won't play it tonight because you don't want me singing along with this, not in this state of mind that I'm in right now. It's almost midnight. And you probably, yeah, I mean, the rendition is actually pretty musically good, but it has a lot of stuff going on about what are the shapes of the orbitals, and it rehashes a lot of the stuff that we just said. So feel free to go watch that now, and maybe I'll supply a link. But the whole thing is we are almost done with our story of how the shape of the periodic table works. There's one thing we haven't talked about yet, and it's the fact that electrons have spins, and two electrons can actually fit in the same orbital if they have opposite spins. Now this is a weird quantum mechanical thing, but this is just a fact that we've observed. And so that means that the 1s level can actually hold 2 electrons. And so the electrons go 2 by 2, okay? So that means that hydrogen and helium both just have a 1s level that gets filled up. And then lithium has a 2s level, and you add the higher energies on as you add on the electrons. The electrons go to the lowest energy first, and so you only get to like 2p once you have like 5 or 6 electrons in the first place. And then, of course, there's all the weird rules about things that go slightly out of order, and you know, the Aufbau principle and stuff like that. But the important thing is that because the electrons pair up, it means that it takes us 2 atoms. As we add on protons, we're going to keep the 1s orbital for the first 2 elements. Helium has just a 1s. Lithium is the one where we add the 2s on. And boron here is where we start to add the 2p. So because electrons go 2 by 2, that means as we add on electrons and we add them onto atoms, we're going to add them on 2 by 2 as well. But with these rules and these boundary conditions, we actually can make a periodic table. So the periodic table comes out of quantum mechanics, and that is the main point of what I want to say tonight. Remember that we have these possibilities for n equals 0, 1, 2, or 3. We have these different possibilities. Oh, and by the way, technically n equals 0 is the way that you really should do it for 3D math. I was sort of going through a few little things. I think that's actually on the previous slide. But the main thing is, look at the possibilities that you have right here. As you add on L possibilities, your M sub L possibilities go up by odd numbers. So N just goes up by 1, L just goes up by 1, but M sub L goes up by odd numbers, 1, 3, 5, 7. 1, 3, 5, 7, like the orbitals that we showed you. And so from this fact, we can actually build a periodic table. Okay, and remember that we have to double it. We have to do 2 times it. But if we take this and we do boxes, let's build boxes in the way that a periodic table would be built. As you're adding, as you're going to the next element, you add a proton and you add an electron to balance it out. So those electrons actually form the shapes. There's 1 possibility, then there's 3, then there's 5, then there's 7. We have to double it because there's 2 electrons in each orbital. But then we can, once we have this, this is actually a periodic table. but you just don't know it yet. What we have to do is we spread those around and we shift those out. And remember that these are just the new possibilities. Every time we move up a level, we keep the old possibilities. So now that we spread them out, we can add on. This is the 1s, so this is the 2s, this is the 2p, 3s, 3p, 3d, and then we can stack those together. And we have, because there's no more room, we could fit it if we had a super wide screen here, but we have the 4f levels down here. Now if we just move those around like this, we just shift around the D block and the P block to be like that. Oh, and we move that one over because, well, various reasons, that's helium, and so it goes with its friends on the other side. But you see how from right there, we just basically fill in all the gaps, and we've made a periodic table. The periodic table has a 2 block, a 1 times 2 block. It has a 3 times 2 or a 6 block on the right, and it has a 5 times 2, a 10 block in the middle, and at the bottom it has a 7 times 2 or a 14 wide block. That is part of where the periodic table gets its elegance from. It gets its shape from quantum mechanics because these are the boxes that electrons can fit in, and so these are the shapes that atoms can take. So the only real difference is that we had to shift some things down. Again, that's the Aufbau principle at work, and we're not going to talk about exactly how we did that. We're going to talk about the widths. And the widths make perfect sense if you count them up, 1, 3, 5, and 7 times 2. So the only way to expand the periodic table is to add more protons. And you have to add neutrons to balance it out. But again, that's physics. Chemistry is really concerned with charges, so I'm really mostly concerned with the protons. As you add more protons, the big nuclei have to hold all these positive charges together, and so it gets more and more unstable. There are forces that hold the nucleus together, but when you're cramming in more protons there, and it gets bigger and bigger, it gets harder to hold together. So it turns out that iron, which isn't that big, is the most stable nucleus. Once you get bigger than iron, then you start to get more and more unstable, and the bigger you get, the more unstable you get. Here's an example, and you probably hear about them creating new elements, and they've just named those new elements. This is actually from before they named the new element, but this is when they created a new element. And the way they do that is they make very small amounts of these elements by shooting protons at big nuclei and hoping that some of them stick and survive for like a nanosecond, long enough for them to measure it. These are not the kind of things that you're going to really do chemistry with. You're not going to build anything out of something that has a nanosecond half-life. So that means that, yeah, the only way to expand the periodic table is to add on to it, and the only way to add on to it is to make something super unstable. So it's not like you're going to make a new element, at least with the physics that we know and understand. When they have Iron Man, like developing a new element, right? That's how he powers his suit. That always makes me cringe, because you can't do that. The laws of physics get in the way of that. Now, there's a lot of other things that I really should be picking on, but as a chemist, that's the part of Iron Man that really gets to me. You can't make a new element because you can't have half a wave. You can't have half an electron, half a proton. You can't have non-quantized versions of these. You have to have quantums in your quantum mechanics. And you can only count by integers. And life and the periodic table can only count 1, 2, 3, 4. You can only count in blocks of 1, 3, 5, 7. And you can't make half an element. Can't have half a proton. So the main point is the periodic table actually has a lot of rationality behind it. It comes out of math, and it's really based on counting 1, 2, 3, 4. If you knew these things about electrons, if you were super good at math and you could figure out how 3D waves work, that's probably the hardest part. If you knew the mass and charge of protons and electrons, and you knew how they're attracted to protons, and that also the weird last little thing is that 2 electrons with opposite spin can pair up in the same orbital. If you knew those 4 things, you could actually work out a periodic table from just those 4 conditions. You could figure out the periodic table using math and physics alone. In other words, don't go wishing for half orbitals. Of course, you can hybridize, but that's another thing entirely. Don't go wishing for new elements like Iron Man has. There's none. We have to deal with the elements that we have. And so when we look at the path that life took, we have to find the path through the elements that we were given. You know, there's only so much science that those can do. But the thing is, there's only so much that, science that those elements can do. It's pretty amazing that life resulted from such a simple set of rules that actually you can figure out. We live in a very figure-outable universe. Okay? Given these parameters, there's no other periodic table possible. And so that implies that in this universe, at least, we've got one periodic table, we've got this set of elements, and this set of abundances for the elements, roughly. And that argues to me that there's this path for life, that the book that I'm writing is the same book that somebody else on another planet would write. There's a lot of caveats to that, and I'm not 100% certain, but I'm just impressed with how simple this path is. And if we can't have another periodic table, and if the periodic table shaped life, then maybe this is the universal path for life. Whatever it is something that we can figure out a lot about, and we can understand a lot about, and we can look back on history and we can see what it happened. So it's something that is, in a word, rational, something that makes sense. And like Einstein said, one of the most amazing things about the universe is that it makes so much sense. He didn't use those exact words, but it's too late right now for me to actually quote it, but you can look it up. He did say something about that. The comprehensibility of the universe is one of the most amazing things. And that's the note I would like to leave you on tonight. And so it's time for me to go to bed. I will see you tomorrow in lab.